Hello everyone, we are the Team 9. This week we will introduce wind conditions and thermal comfort in the stadium. The wind is very important for a building. First, let's look at how the wind is formed.
Whereas wind that travels around angular surfaces or steep slopes becomes gustier and more turbulent. The wind can also stay turbulent long after passing a significant obstacle. This can be called the turbulent zone or wind shadow. For some obstacles, the wind can become turbulent well before reaching it. One generic estimate is that the turbulent zone is 7 times the height of the obstacle on the downwind side and 3 times the height of the obstacle on the upwind side. Therefore, taller obstacles create larger turbulent zones. The reality is far more complicated and depends on a number of factors. The shape of the object is very important. Gentle slopes with a smooth surface can create negligible turbulence. An angular shape or steep slope, however, creates a far larger turbulent zone. The total number of wind obstacles is also critical. The turbulence from a lone object can disappear quickly. It has clean wind on all sides, which helps to remove turbulence. However, with numerous obstacles, the turbulence will last far longer. The wind deflections can combine together. Another key factor is the wind speed itself. When wind speeds are higher, the gusts are stronger and carry further. Ultimately, your best bet is wind that approaches over open ocean. The wind's approach is then clear of obstacles. To be sure, you should walk to the launch area and feel the wind. You should be able to feel if the wind is changing. Obstacles can also alter local wind speeds. When wind is forced into a narrower space, the airflow is forced to speed up, and wind moving into a wider space will slow down. Wind passing between two mountains, for example, will speed up. Or wind climbing a slope will be forced to speed up. This is why it might sometimes seem windy enough when you arrive at the top of a beach or sand dune, but when you walk to the water's edge, the wind's not so strong.
So it's necessary to combine the boundary layer wind tunnel and numerical modeling studies was carried out to assess spectators' comfort levels for the stadium, with wind tunnel measurements being made for the external plaza surrounding it, and for the concourses and the key seating areas within. These wind speeds were used in assessing pedestrian safety and comfort in and around the stadium. Wind conditions in the stadium and the external plaza are generally suitable for stalling or for short periods of standing or sitting. No areas would be uncomfortable for stalling. The wind speed at the game is also very important. IAAF provides for all track and field records of 200 meters and below. If the average wind speed of the athlete is over 2 meters per second in the direction of travel, the record will not be accepted. In addition, a wind speed measurement is also developed to develop a suitable storage for the stadium. The results showed wind conditions in the athletic arena during the summer months to be, on average, very benign. Next, let's take a look at the thermal comfort.
Designing for thermal comfort. There is no one-size-fits-all recipe for thermal comfort. Solutions vary depending on the local climate, as well as the type of activity performed by the building users. The building envelope acts as a filter between the exterior and interior climates. Designing it efficiently implies the consideration of 5 main factors. 1. Insulation reduces heat loss during cold seasons and heat gain during warm seasons. 2. Solar gain is influenced by the building's insulation levels, its shape and orientation, the window to opaque wall surface ratio, the type of glazing, shade or shading devices. 3. Thermal inertia varies according to the mass and material of a building. High inertia envelopes give more internal temperatures in the face of outdoor temperature change. 4. Airtightness and ventilation enable the control of air exchanges with the outside. A well-designed building envelope can dramatically reduce the need for mechanical systems required to provide thermal comfort, so reducing the environmental impact.
As shown in figure, the surface temperature of the roof and steel members on a typical day during the Olympic Games. The maximum temperature of the acoustic ceiling and the roof clad dim could increase to 38 degrees during the daytime, with the roof steel members as hot as 47 degrees due to the strong solar radiation effect and the heat absorption properties of steel. With the temperature and relative humidity distribution and air velocity vectors evaluated by CFD, the thermal comfort conditions at the spectator area of the stadium were assessed. During the design process, the following optimizations were performed to improve the thermal comfort level cost effectively, without any active mechanical system. For example, increase the distance between the highest seat and the false ceiling from 2 meters to 8 meters, and reduce the area of the ultra-transparent ETFE membrane layer. As feature, the optimization proved effective in terms of the thermal sensation index. The Beijing Olympics were promoted as green. A green building design does not only aim for energy efficient or energy conservation solutions, but also for a high level of comfort within the building. To make Beijing National Stadium green design work, the thermal conditions inside was critical, especially when in its Olympic mode with up to 91,000 spectators. Next week, we will continue to introduce building services design. Thanks for watching.